morning. Thanks for joining us on another TPC training webinar. Today we're going to talk about all things variable frequency drives. So we're going to take a very high level look at all things VFDs. A couple of housekeeping items. Some of the most common questions we get are, can we get a copy of the presentation? Absolutely you can. You'll receive a follow-up email at the conclusion of the webinar. Please just respond back to that email and just let us know that you want a copy of the presentation, and we will absolutely get that to you. Also, we are recording the webinar, so if you need a link to that recording in case somebody at your facility happens to miss it, please let us know that as well, and I will be happy to send you a link to that recording. This will be our last webinar for 2018, but look for another series of webinars to come starting in early 2019. Without further ado, I want to turn things over to our presenter, Joe Doolittle. Joe?
Yeah, good morning, everybody. This morning's presentation, like John spoke about, is variable frequency drives. I think just about all your facilities have these very unique motor control systems. And over the next half hour, 45 minutes or so, we're going to go over the basics of the drives. And certainly, if you have any questions whatsoever, go ahead and text them over to John, and we'll address each and every one of those questions. It's really, really important that we answer all of those questions for you. So any questions that you may have, be sure you send them over to John, and we'll get those answered for you right after the presentation. Introduce those questions to John. Let me just make sure we don't have any audio difficulties. Okay, good. So if you have a requirement for instructor-led training or on-site training or online training, just give John a holler. He'll help you out with that. Having said that, just a little bit about myself. My name is Joe Doolittle. I'm a retired U.S. Navy Chief Electrician. I'm from Reno, Nevada. I've specialized in the 60 hertz and also 400 cycle world with the U.S. Navy. I was on 4 different ships. One of the ships, USS Halsey, it was a CG. I was also on a frigate, USS Truett. I was also on a USS Stump. It's a Spruance class destroyer, gas turbine type. And as you can see from the picture there in my old house, I was on the USS America for 3 years. In addition, I did submarine repair. I was a non-nuclear subsafe level 1 electrician. So I understand the power system industry quite well. So let's get on to the variable frequency drives. All of your plants, whether it be manufacturing, commercial, very rare residential, has variable frequency drives. They look kind of intimidating when you first look at them, but they're really quite easy once you interrogate them a little bit. If you look at some of the applications, whether it be conveyors or compressors or extruders, and if you don't know what an extruder is, it's a plastic manufacturing or printing presses, tumblers, polishers, and even I mentioned to a friend of mine the other day, Elon Musk, he did pretty good. He put one of these drives in an electric car, and if you look at the heart of an electric car, it's got a variable frequency drive in it. Winders, lathes, electric trains, boring machines, wheel grinders, all of these type of machines have variable frequency drives. It's a very unique skill set to have one of this particular skill set. And over the next half hour or so, we'll make sure you have an understanding of these particular units. In particular, that variable torque application the air conditioning and refrigeration industry certainly use these to maintain your temperatures and your pressures and your levels and whatnot. So it's such a wide application in the 21st century. Variable frequency drives, if it moves, if it goes up, if it goes down, if it goes fast, if it goes slow, has one of these variable frequency drives. So this particular part here, if you have a pen and paper, if you could, I'd like you to draw just the upper half of this. This is the heart of the drive right here. This is the main power system. So if you could, go ahead and draw that three-phase AC full wave bridge rectifier. Those are those 6 diodes that you see there on the left-hand side. And it's important to draw this and understand this because this is the heart of every variable frequency drive. There's some variations, but this is a very, very common circuit. So go ahead over the next few minutes and go ahead and draw that. As you can see, as you're drawing it and I'm speaking, you can see that it changes AC to DC and then DC to AC through that full wave bridge rectification. If you had an oscilloscope, and we do have an oscilloscope, we would be able to see that traditional sinusoidal waveform on the primary side, on the left-hand side, converted to DC. It's really important to know that it's AC to DC. It's very predictable, that DC bus voltage. And if you could, make a note in your notepad there that the DC bus voltage will be much higher than the AC bus voltage. For example, and this helps when you're troubleshooting. This is very, very important. We'll get to the display and the control circuits there in just a second. If you multiply your AC voltage times 1.414, that'll be your DC bus voltage. So in your troubleshooting, if you want to know the health of the power section of this drive, your drive, it's good to know what the DC bus voltage is. So for example, if you had 480 volts on the primary, you ought to have about 680 or 679 volts DC on your DC bus. And we'll be able to get to that DC bus through the display. As we move through the circuit, you can see that the AC to DC on the converter side, and then it goes DC to AC on the inverter side. And those 6, let's call them IGBT. So if you've drawn this system, mark an arrow there at the blue section. Those are, it's kind of a long word, and not to worry about it. It's an insulated gate bipolar transistor. Don't get caught up into the words or the symbology on that. It's nothing but a big giant switch. So what we do on this variable frequency drive is we take AC, we convert it to DC, and then we convert it back to AC. And so just for you folks using multimeters and whatnot, the output of a drive is not a traditional sinusoidal waveform. I know these terms may be new, but on the left you have input power, traditional sine wave that you see there, but the output is a pulse width modulated signal. I'm only going to use a couple of new terms today, and that happens to be one of them. So the number one term is an IGBT, insulated gate bipolar transistor. It's nothing but a switch. And you can see that there's 2 per phase. You have A phase, B phase, and C phase. So it takes that AC power, converts it to DC, And then from that DC power on each of the phases, converts it to a pulse width modulated signal. It kind of looks like a square wave when you look at it on a scope, and we have a scope, and I can show you what that waveform looks like. So from a troubleshooting aspect, we've got incoming power, and then we have DC, and that DC is converted over to a pulse width modulated signal. I guess what I'm saying is the input is traditional, the output somewhat of a square wave. And I might add also, your multimeters may or may not read that output signal. So it's really important as we look down at the display, the ability to go through the display and see what you're looking at. Not all multimeters will read that pulse width modulated signal. And during the course, you'll see we'll talk about RMS, root mean square, and some other calculations that we need to go over. But let's just one more time take a look at this particular circuit. This is your drive. We got AC, converts it to DC, and that DC back to that pulse width modulated signal. And if you look close at this circuit here, if you replace that capacitor that you see in the center there with batteries, for example, it would really look like a UPS system, doesn't it? If you replace that capacitor with solar panels, it could be a solar system. This particular circuit is a very, very common circuit in the power industry, whether it's variable frequency drives, UPS system, or a solar photovoltaic system. So this is a very, very common system. I ask that you write it down. You're going to see it again, whether it be in the drive world, or whether it be in the UPS world, or whether it be in the solar photovoltaic world. As you can see there, below in the yellow, you have control circuits. If you saw the tails on those transistors, that's the vertical line just opposite of the arrow there. Those tails or those control circuits, or let's call them firing circuits. Those firing circuits go down to the control circuits, and that's what gives us our speed control. As much as we mentioned earlier, as much as we turn those inverters on and off, that's where the control circuits come into play. And we're able to visually take a look and see how much they're turned on or turned off. There's one other thing I might want to mention on these particular units. You notice the arrows there, that means polarity. And these things are polarity sensitive. When you jump your car with another car, it's polarity sensitive. If you get the polarity wrong, that's not a good thing. And so the same thing with these variable frequency drives. You're going to learn in the next few slides there, getting the polarity right is very, very important. And you can do that with a multimeter. And as you can see on this particular slide here is the display. We'll be able to interrogate this particular system, whether it be an Allen Bradley, an ABB, a Cutler, Hammer, whoever the manufacturer is, will be able to go through your particular drive and see how the health of the machine is doing, whether it's input voltage, output voltage, current, torque, acceleration, deceleration, rotation, and a variety of other parameters. So using the display is very, very important. And so if you look at the left side there, you'll see a serial communication port, an RJ12 jack. Now, it could be, doesn't have to be an RJ12 jack. It could be a USB port or an RS485 recommended standard or 232. So we'll be able to communicate with the computer too. So we can use the display very easily, but then again, it's a little easier with the computer. I might just add that. So being able to communicate with these things are very, very good. There on the right-hand side, the operator controls. So whether you're operating it from an external source, whether it be push buttons for a conveyor, or maybe limit switches for a water tank to start, stop, or control this particular drive. So you can see just from the one slide right here, we've got AC coming in, converts it to DC, and that DC bus, I might add, is always going to be higher. It's 240 volts, and it's going to be 300 and something volts. If it's 480 volts, it's going to be 678 or whatever the calculated value it is. So when we're troubleshooting, and that's one of the things with these drives, is that we must know it's the ability to know what you're supposed to get before you look at it on the display. So the long and short of these drives, AC to DC, DC to AC, the output is a pulse width modulated signal. Now, they're kind of misleading you when they say variable frequency drives. It's also a variable voltage and frequency drive. So if I had 480 volts and 60 hertz, just as the big picture here, and I know we've gone over a lot in the last 15 minutes or so, but it's not just a variable voltage or a variable frequency drive, it's also a variable voltage and frequency drive. So if you're qualified to look at your units and operate the display of your units at half speed, you're going to note on your display it's going to be half voltage. So say, for example, if I have a 480 volt system and I'm running at half speed, you'll note that it's going to be reading 30 hertz and 240 volts. Or if you're at a quarter speed, you're going to be looking at 15 hertz and 120 volts. So it's not just a variable frequency drive, it's a variable voltage and frequency drive. And that's based on what they call the volts to hertz ratio. Now, I know I've gone over a lot in the last 15 minutes or so. So I do encourage you to take this presentation and take the audio and review it, and you'll get the concept. They're not just a variable frequency drive, it's a variable voltage and frequency drive. But I might add that you're able to change through the programming that volts and hertz ratio depending on the application. Okay, so we got the AC to DC, DC to AC, the pulse width modulated signal. Then we also have the display that we can go through. And then we can also use that communication jack too. 10 reasons why we should have a variable frequency drive or use a variable frequency drive. Or just starting current? Absolutely. There's 3 foot-pounds of torque per horsepower. Do me a favor and write that down. 3 foot-pounds of torque per horsepower. So as we increase speed from 0 speed to full speed, if we want to control that current or control that torque, we can do that from 0 speed to full speed. And if you wanted, we could do an equipment speed profile from 0 speed to full speed, and we could take into account pump pressure, temperature, level, whatever the medium might be. Reduce power line disturbances. If I have a large horsepower motor and I start it on a across the line power system, you could, and it does, influence the surrounding power grid. So if you want to reduce that, if you had that particular problem, these things are great for solving that particular problem. Lower power demand, or sometimes they call it demand factor. When you start a large pump, blower, motor at a large facility, maybe it's a large manufacturing facility, you can get charged a demand factor or a demand charge. Having said that, did you know, and I'd like you to write this down, there's 746 watts in a horsepower. So do me a favor and write that down. 746 watts in a horsepower. So when you look at your electric bill, you'll be able to see that reduction in power demand or demand factor or demand charge if you're a large facility. Having said that, you have to know what a kilowatt hour is. So a kilowatt hour, if you take 10 100-watt light bulbs and put it on the wall, that's 1,000 watts. That's a kilowatt. So a kilowatt hour is 1,000 watts for an hour. Now, I don't know in your particular area. In Hawaii, for example, the power is very expensive. In some of the northern states, it's not so expensive. In the south and Florida, kind of spendy over there. So let's just use 10 cents per kilowatt hour. Now, it'll vary. In some areas, 18 cents per kilowatt hour. Some places, 7 cents per kilowatt hour. It depends on your particular area. One of the things that we like to do with these drives is save a little bit of money on our power. And now we understand what a kilowatt hour is, and we understand that there's 746 watts in a horsepower. We'll be able to calculate what it costs to operate our equipment. So let's just take, for example, a 10 horsepower motor. So we said 746 watts in a horsepower. Perfect. And at 10 cents per kilowatt hour, I don't want to go too fast, but at 10 cents per kilowatt hour, it's 7 cents to run a 1 horse, or 7.74 cents to run a 1 horsepower motor. If we did our calculations, let's see what it costs to run a 10 horsepower motor for an hour. It costs about 74 cents an hour to run a 10 horsepower motor. So to run it 24 hours, it costs about $18 for a 10 horsepower motor. And knowing how much these things cost, and I did some quick calculations, and at 10 cents per kilowatt hour to run a 10 horsepower motor for a month would be approximately $532. So having said that, now bear in mind, different areas, it costs more or less depending on peak, mid-peak, and off-peak time. I was just using 10 cents per kilowatt hour. But it would be interesting in your particular area to find out what it costs per kilowatt hour to run your particular equipment. If we can save 10 or 15% by making some adjustments to this variable frequency drive, we'll be doing our due diligence for the operation of our particular plant. So we can reduce that power demand using a variable frequency drive. Control acceleration. For example, each application is going to be a little bit different. If you're a ski lift, for example, you want to slow your acceleration, maybe from 0 speed to full speed, and take 45 seconds. But if you're operating a pump or a blower and you want to change that acceleration to 3 seconds, you can do that also. So controlling the acceleration is very easy to do. Adjustable speed, maybe you want to operate it by hand. Maybe it's a conveyor if you wish. You'll be able to control it either at the keypad or remote operation. It depends on the application. You'll be able to set these things up very, very easily. Adjust the torque. We already said 3 foot-pounds of torque per horsepower. Maybe you're winding wire or taking tension on something. You'll be, based on that earlier discussion, the volts to hertz ratio, you would be very easily be able to adjust the torque. And not only adjust it, but set limits also. You don't want to over torque something. So with a drive, when you program them, you'll be able to adjust whatever torque limit that you wish. Control stopping. Maybe you need a dynamic brake. Maybe you want to coast to the stop. When we program these particular drives, whether it be by the keypad or by the computer, we get the information either from our own design people or from the engineers to set it up. This is going to be part of a total system. So the drive itself is part of a total system. It's not the conveyor, but it does drive the conveyor. Energy savings. We've talked about that briefly. How much it costs to operate, and if we change something 1 or 2%, or the time of day, or the speed, or the power consumption, we'll be able to see and realize how much money we can save. If we pick a date at the particular time of the month and we make a change, we'll be able to realize a power savings if we do a very deliberate change with regards to these drives. Reverse operation. Having said that, maybe you don't want your system to go in reverse. You can inhibit that particular operation, or you can enable that particular operation. So forward, reversed, up, down, fast, slow. You have total control of the system once we program the system. Perhaps you don't have a drive at all. You want to change over from a mechanical system. You'd have to take some torque calculations, and there's calculations that we can calculate torque based on motor speed. So we'd have to convert or size a drive specific to your particular application. A lot of reasons, and there's even more reasons. And the next one, this particular reason is kind of cool too. With that drive, you'll be able to, if you don't have three-phase power and you need three-phase power, you can use a drive, and it's allowed by NEC to convert single-phase to three-phase. If when we drew that system, that diagram from the very beginning, you could see that you can take single-phase power and convert it to three-phase. A lot of farm folks do it that don't have three-phase power readily available to you. You have to oversize the drive a certain percentage depending on the application. You don't get something for nothing, but you can use a drive to convert single-phase to three-phase. One of the things we have to remember when we do that is the output of the drive is going to be a pulse width modulated signal, that square wave, if you will. And I might add one other thing also, that variable frequency drives oftentimes require an inverter duty motor. So, and the question might be, do we need an inverter duty motor? The NEC says you should use an inverter duty motor. You don't have to use an inverter duty motor. You can use a regular motor. One of the drawbacks of using a regular motor, though, is it's not designed to run at lower speeds. So just keep that in mind. It's all about the application. So your application may require those lower speeds, and so therefore at lower speeds you wouldn't want to use a non-inverter duty motor because the pitch of the blade doesn't provide adequate cooling for the motor. So you can use a non-inverter type motor, so it's kind of application specific. So you can use a non-inverter duty type motor, but we have to make sure that we don't go below 50% speed. So, but it's all about the application. as far as sizing and these things. So you can use an inverter or non-inverter duty motor on an inverter. And the difference between, that might be the question, the difference between an inverter duty motor and a regular motor is the insulation. That pulse width modulation signal I spoke of earlier sometimes presents transients or power spikes. So that insulation type, that resin-based varnish that's on the motor is somewhat spike resistant. It's it's a high integrity varnish to resist those spikes. In addition, it's a higher efficiency. So you can use a non-inverter duty motor, but there's drawbacks to that too. It doesn't have that spike resistant fire, and it's not quite as efficient as an inverter duty motor. And like I said, farmland and other applications that don't have three-phase power can certainly use a drive to convert single phase to three-phase. One of the things I've noticed over the years is just operating the keypad. Some of these drives can be somewhat intimidating on the keypad. So one of the things we really have to understand, whether it's this manufacturer, an ABB or an Allen Bradley or Hammer, whatever manufacturer it is, I've found that a lot of folks don't understand the keypad. So what I would ask, and we could go through this keypad and you can see there it's got a program button. The display button is really important. Some of them have a mode button or an enter button or a program button, but nonetheless, you'll be able to go through the display. If you don't do anything else after this particular seminar, if you're qualified, we have to make sure we don't want to operate these particular drives if we're not qualified to do so, is go through the display. And once you go through the display, let me just go to another slide real quick. On the display, you'll see all the little bits of information that you can pick off of this thing. You got the actual operating frequency. And unfortunately, if you notice, look at number 7 down there. It says PID set point. And unfortunately, with most of these displays, and I'm going to say 80% of these displays, it's not going to be plain language. You're going to have different addresses with different nomenclature on there. It's going to say U's and T's and Z's and different numbers, and that has to do with memory storage. So just going through the display is very, very helpful. So the actual operating frequency, the RPM, the scale frequency, that's just a multiplier. The different current levels, the percent of load. And you say percent, how does it do that? It calculates the percent of load. Output current, what the rated current is, then you can set these up. So if you put the rated current at 5 amps and it's running 2.5 amps, it's going to tell you the percent of load. Setting these little rascals up is very, very easy once you know the addresses in which you're supposed to set them up with. Not difficult, it just takes a little bit of time to go through and those unique addresses to program these. And so if you look at that DC bus voltage earlier, I said that the DC bus voltage is a great indicator on that health of the machine. So if you don't walk away with anything else today, just know that the DC bus voltage is 1.414 higher than your input voltage. Now, we could talk about PID, proportional, integral, and derivative. It's too short of a seminar or webinar to talk about PID set point. That's quite a lengthy conversation and takes an hour or two or so or better to talk about that. And so at the very bottom, you have set point. Set point is different than actual. Where you set it and where it is two different things. And we can go through that maybe at a later date. But so the display, I guess what I'm saying, is your friend. And this particular drive has 10 or so different displays. ABB, Cutler Hammer, and those others have many, many more different displays. One of the last things I want to talk about is how to wire one of these little rascals up. Not difficult, but we have to understand what our digital inputs. Do you see the DI1, DI2, DI3, DI4? Those are digital inputs. There in the lower left, it's A1. Those are analog inputs. The majority of your analog inputs are going to be a 4 to 20 or a 0 to 10 volt signal. You got to determine it. We can select which one of those signals we want, depending on the application. If we're going to go a great distance, we certainly use a 4 to 20. The short distance away, and I'm talking about where the sensor is or where the tank is as opposed to where the drive is. So 4 to 20, you can go 1,000 feet. A 0 to 10 volt signal, we'd want to keep that a little bit closer. So you can tell on the left side how to control this. Forward stop, reverse stop, external fault, multi-speed. That means a dedicated speed. You want this, you hit that switch, you want it to go 14 hertz. Perfect. We can set it up for that. There on the right-hand side, you can see that we have what they call multifunction output contacts. Maybe you want to satisfy a fire alarm system. You need to know that this system is running and up to speed. You can program these multifunction output contacts. When the drive is at speed, want these to open or close. So those two are programmable. Each one of these digital inputs or relay outputs are all programmable. There's a buffet of different, maybe you want to know if there's a fault. Maybe you want to know if you're under speed. Maybe you want to know if you're over speed. Whatever the case might be, you'll be able to program these things, whatever your application is. Maybe it's just an indicator light. You want to know when it's running. You want to know when it's not running. You'll be able to do that also. And you'll see on that AO, the analog output. Maybe you have a SCADA system, a supervisory control or data acquisition system. You need to know some sort of linear or some sort of proportional output based on the speed. A 0 to 10 volt output. Some of them have a 4 to 20 output. A lot of them have a 0 to 10. You'll be able to provide that to your system. Having said that, this particular drive and all the other drives you can tie to your PLC system too. Programmable logic controller. So you can get your digital inputs either from a switch or a PLC, or you can use your relay outputs and tie it to the PLC. So these are very interchangeable. Whether it's digital outputs, analog outputs, digital inputs, or analog inputs, they can tie right to your SCADA system or your energy management system. And there again, have that communication port. It might be an RJ12 jack or a 232, and you're going to find the software is very easily and readily available for the majority of your systems. Sometimes it's free, sometimes it's not free, sometimes you have the cables, sometimes you have to purchase the cables. Nonetheless, whatever manufacturer you have, the software and the cables are going to be unique to that system. So if you have an ABB, it's not going to work on a Cutler Hammer or a Baldor. So each one is unique. And it takes a little bit to get the software and understand the software. They got some great features and functions on the software, I might add. And this is just kind of an example of some of the settings. And you see that P200, that happens to be an address. All of these things are addressable. Each of the parameters are addressable. So each of these programmable addresses are addressable. So let me go to another one here. Go to the keypad. There, I'm going to go back to the addresses. But you can see on the keypad, although it looks really kind of busy, it's really not busy. You got the LEDs up front and the LED indicators, what mode you're in, the program button, the display button, the forward reverse button, and the potentiometer button. So once you get your keypad, whatever it is, and I'm going to make a recommendation if you could, is just take a look at your keypad, understand your keypad. Take 15 minutes. Whatever manufacturer you have, ABB, do I have another ABB there? I don't, but whichever it is, some of them, Yaskawa is always a challenging keypad, but challenging doesn't mean impossible. Just means we need to take a little bit more time with it, that's all. So don't be afraid to take a look at the keypad and all the different functions. And the same thing with the terminations that you've got right there. On the 9, you got, you know, we looked at the schematic a moment ago, and we saw some terminals. And so those terminals are well labeled. You can see on the right, or at the bottom on the right, our relay outputs and our digital inputs. Even have a couple of dip switches at the very top. Understanding what you're looking at on these things is half the battle. So if you go through and you find, so at the very top, I don't know if you can see if you look close, that's a selection. Do I want to get a voltage signal to this thing, or do I want to get a current signal to this thing? Do I want a 485 connection or a 232 or whatever the case might be? So we know where to hook these up. We've taken a look at the keypad, and over a short period of time, you'll understand your system. So, like it says right here, sometimes you got to look under the hood. But let me caution you, my friends, you must be qualified to do this type of work. This is not for the unqualified folks to open up these voltages, and PPE is very, very important when operating and opening the covers on these things. So the appropriate PPE, and make sure you're qualified to look under the hood on these things. There's that ABB Drive there. And so that's just another address at 97 or 9907. I believe that's acceleration. So each one of these programmable features on these things have an address. Just a matter of picking up the book and finding out what that address is. Very, very easy once you spend a few minutes doing these type of things. Understanding drives, well, drives, you have motors, and so motor theory is very, very important. So whether it's single phase or 3-phase motors, it's just very, very important to understand motors and how to test motors. Most of our stuff is 3-phase motors, but it doesn't have to be 3-phase motors. It could be a single-phase motor also. ABC, 1, 2, 3, black, white, red, whatever your color, Y or delta, and each of those particular configurations are depending on the application, whether it's Y or delta, or whichever your voltage happens to be. One of the things I might add also is that we mentioned earlier that if you do use a non-inverter type motor, you'll have to select this particular address. So they recognize the fact, and let's read through that. When using this setting with drives that are not designed specifically for drives, motor and shaft fans provide poor cooling. So they know that. And I think I said 50% speed. They say 40%. I try not to run it down that slow, but you can 40%, but I keep it 50%. No need to test the cooling of these things. Understanding speed of motors. Remember, there's two different things going on in a motor. There's synchronous speed, that's the speed of the magnetic field, and actual speed. Two different, and the difference between those, and do me a favor and write this down too, is slip. So that's the difference, and there's a calculation for that. We have to be able to calculate synchronous speed and rotor speed, and there's a little bit of math involved. It's not that big a deal, but we would not want to exceed 3 to 5%. So there's a few calculations going to be involved. So there's actually a handful of calculations with regards to these particular drives. So there's synchronous speed and rotor speed, not to exceed 3 to 5%. No, at the very beginning, I mentioned that volts to hertz ratio, and just want to kind of close this thing out a little bit. We started out at AC to DC and DC to AC, and if we don't maintain that certain volts to hertz ratio, it can affect motor torque, temperature, speed, noise, and I might add, we're able to, that high frequency noise that you hear as a result of that pulse width modulated signal, we can control the noise on that too. It's an address that we need to change. Control current draw, and there again, there's a little bit more math involved in some of this. So listen, I just want to thank you for your time this morning. And if you have any questions, go ahead and present them to John. I'll be more than happy to answer them for you.
Yeah, thanks, Joe. We are running a little low on time. We do want to be respectful of everybody for their time this morning and leave enough time for some questions and answers. So on the right-hand side of your bar there, you'll see a little question box. Just submit a question through there, and we'll get that answered. So we do have a couple of questions already. The first question is a little lighthearted, Joe. They're asking if you have any relation to the famous Jimmy Doolittle of Doolittle's raid infamy. Any truth to that, Joe?
Can you hear me, John?
Yeah.
Yeah, so if his middle initial, and if he's out there, if you know, if his middle initial is C, then the answer is yes. But no. So I've been asked that a couple of times, but no, if his middle initials, I did a little research, so no.
All right, next question. Early in the presentation, Joe, you talked about a number to multiply by to figure out the AC. Could you run through that real quickly again, please?
Yeah, so here's, and for everybody that's still online, if you want to know what your DC bus voltage is that the question, John?
They specifically mentioned AC, not DC.
So I think this is what he was alluding to, is that if you want to know what your DC bus voltage is on your drive, you take the AC voltage and multiply it by 1.414, and you'll get your DC bus voltage. That's the number. That's an important number to remember. So if you take the AC voltage and you want to know what your DC voltage is on your DC bus, very important, and that tells you the health of the machine, is 1.414. And so just so you know, where does that number come from? If you look at RMS, and remember, all of our meters measure RMS. If you look on the top of your meter, it's an RMS meter. And RMS is 0.707 of P. Certainly is. That's RMS. So because we're going to chop the top half and the bottom half, it's RMS times 2. So 0.707 times 2 is 1.414. You take the AC voltage, multiply it by that, that's what you get DC voltage, and that's what it is.
All right. This next question, it's lengthy, so I'm going to just read it verbatim. All right, Joe? It goes, do we have the actual line voltage on the controller's termination? Meaning, let's suppose we run a 4160 volt motor until we have that much on the L1, L2, L3 terminations?
Well, that's incoming. Did he make an error? He might have been referring to the outgoing. Read that question again, because he said you said L1, L2, L3,
Right.
and if he's talking about the output voltage, the answer is yeah, it'll go all the way to the top. If he's
Okay.
talking about output voltage, the answer is of course.
Can you talk about any differences between a soft start device versus a VFD, Joe?
Yeah, it's how they are set up. I think his question is, can you use a VFD for a soft start? The answer is yes.
Okay.
Yeah, it depends. It depends how each application is going to be a little bit different. So the basic difference between a soft start and a VFD is a VFD has many more features. A soft start is just a slow accel. That's all. It's just VFD has many more features, and I've seen them use drives as soft starts. So.
Okay. Next question simply asks for some key points for commissioning.
Yeah. So one of the key points for commissioning is do a speed profile. What I mean by that is, if you're commissioning something or somebody's commissioning something for you, is make sure that the motor is set up properly. That means that the drive, the voltage, frequency, and speed, and maximum RPM is proper. These don't set up themselves. They have to be set up properly. So it may take a little bit of time to make sure that everything is set up properly. Number two, you'd want to run a complete, what I call a speed profile, from 0 speed to full speed. So at 10 hertz, write down the voltage, write down the load. So if you're pumping water, so at 10 hertz, at the bottom of the speed range, write the voltage down and the current. At 20 hertz, write the voltage down and the current. And at the same time, write down the pump pressure. At 30 hertz, write down the voltage and the current, and then whatever you're pumping, blowing, or heating, or level, or whatever the case might be. So the key thing is go from 0 speed to full speed and take a set of readings at 5 hertz or 10 hertz intervals. And then that way, at the end of the day, you've got a complete speed profile. Now, the cool thing is that if you happen to have the software, you can run your pump, motor, blower, whatever you're doing, and it'll record it. So a lot of the software has some pretty cool trending software as far as commissioning goes. So either you can take the readings manually, and something else I might add too, keep in mind the ambient air temperature. Here in Phoenix, our temperature is quite high here, so and that will influence your drive. So yeah, do a speed profile from 0 speed to full speed, and make sure that it's set up properly, and make sure that it's wired. And one of the key things too, and I wish I had brought this up during the thing, is torquing all the screws and terminals. So no longer is tight right. Everything has to be torqued to the proper specification. So ensure that you do a speed profile, ensure that it's set up properly, and ensure everything is torqued properly too. And you're at the right temperature. And it's sized properly too. So sizing, speed profile, and temperature, and torque values of those terminals.
All right. Joe, what are some of the downsides of VFDs besides any costs that are associated with them?
Downsize of VFDs is operating at lower speeds. So they advertise they go to lower speeds. There's no question about that. But probably running at a lower speed for a length of time is probably one of the cons. Is running at lower speeds, and also being temperature sensitive. These things are only good, and you know, I'm going to throw a number out there, 104 degrees. So they don't like heat. They're very good units, but you get up around that 104, better than 104 degrees, or I say 104, but we wouldn't ever want to run these above 92, really. But they're temperature sensitive and running at low speeds.
Okay. Next question, Joe. When you said every 1 horsepower is 3 feet-pound of torque, is that only during start to speed up, or is that continuous?
So each motor has its own torque. So it's foot-pounds of torque, 3 foot-pounds of torque. So each motor has a NEMA design to it. So whether it be NEMA A, B, C, or D. So each motor, and if you look at the nameplate, each motor has a NEMA design code on it. So it's 3 foot-pounds of torque, no question about that. But each motor is unique in its particular torque curve. So whether it's starting torque, running torque, or accelerating torque, that's all based on their particular torque curve. So you'll have to look to see what NEMA, National Electromechanical Association design is. So there's 4 different torque curves, A, B, C, and D. And traditionally, or most of the time, it's design B. So you'll have to find out what your particular design code is to answer that specifically for your application.
All right, thanks, Joe. Here's one about a specific application that somebody's working with. And I'll read it verbatim. It says, we are removing the O-rings from our SGCTs because they are failing, breaking off, and damaging the circuit board. Are the O-rings being removed a big deal?
Hang on just 1 second. Could you repeat that question, please?
Yeah. We are removing the O-rings from our SGCTs because they are failing, breaking off, and damaging the circuit board. Are the O-rings being removed a big deal?
O-rings on IGBTs?
SGCTs.
SGCTs. I'm not familiar with that term. I don't know O-rings and SGBTs. It's a new term to me. Sure he doesn't mean IGBTs?
I don't know. I read it verbatim. But you know what? We will. We're going to circulate that one around the team.
I don't know about O-rings and SGBTs. I'm just I'm in unfamiliar territory.
Gotcha. All right. Next question. How does a B-phase ground affect a VFD?
Bad. These are a B-phase ground, so it would trip a breaker. So
okay.
Not good.
Not good. Okay.
Yeah. So it would depend. So that's kind of a question without any prerequisite information on that. So is it a delta system, a Y system, a center tap system? So generically grounds are bad, but I don't know what type of voltages he's talking about. So generically grounds are bad, but I don't know because there's 2 or 3 or 4 different type of distribution systems, and so I have no idea which one he has. So
right. But generically it's bad.
Yes, sir.
All right. Next question is asking if you could briefly mention about electric fluting of motor bearings.
Well, that's a long story.
All right, so maybe not briefly.
No, well, I'm going to briefly. So this has been going on for about 30 years. This bearing damage caused by variable frequency drive. So certainly there's a lot of white papers and a lot of opinions out there on that that pulse width modulated signal is influencing bearing damage. That's the nut crust of this question here. And so there's a lot of talk and there's been a lot of chatter on it. The best thing I can say on that is if you think you have that problem, take a look and see and use a scope or some sort of spectrum analyzer to see if you actually have a problem. A lot of times you get bearing problems, and everybody likes to say it's the variable frequency drives. So there must be something to it, because the discussion has been going on for 30 years, literally, and I've seen it once or twice. So I think it's a lot of discussion and a lot of finger pointing to the drive. So on rare occasions, in my opinion, and there's a lot of opinions out there, I might add, on this particular subject, is that it does happen, but it's rare. So if you think you have voltages to the bearing, take some readings. If someone says you have induced voltages into the bearings, the best thing to do is take a reading and see if it's for sure. A lot of people say that that's happening, but then you don't see it. So there's a lot of opinions on it, and I've seen it once or twice in 30 years, maybe 3 times in 30 years. So there's been discussion a lot about it. I've seen it once or twice, but I think there's more talk than actual phenomenon with that one.
All right. I'm going to give everyone one more chance to submit any questions. So we're going to wait a little bit to get some in here, Joe. But in the meantime, do you have any sort of parting thoughts or last bit of words of wisdom as it relates to variable frequency drives?
Yeah, absolutely. One of the things is if we are not qualified to put your hands on these things, don't do it. These control the speed of our equipment. So there's one of the rules are on these things: no hoping and poking. You can't be just guessing on these particular items. It's a very unique piece of equipment, and so there's no guessing on these things. So homework is the name of the game. So if you don't know what you're doing, just ask somebody or something.
All right. Well, we've exhausted, I think, all the questions, Joe. If you need a copy of the presentation, you're going to receive a follow-up email at the conclusion of the webinar. Please just respond to that email and just request a copy of the presentation. I'm happy to send it out to you. Also, if you need a link to a recording of the presentation, I have that as well. So just let me know if you need that as well. But that about does it for our time. I do want to thank everyone for joining us today and for the entire year. We've done about 10 of these here in 2018. We look forward to getting it back going in 2019 with a whole new series of webinars. We're trying to keep things topical and bring you guys topics that are of interest to folks in your arena. So thanks again, everyone. Take care and have a good day.